We are ready to start the technical program. This was the official opening of the conference. So we are ready for the next and first keynote by Professor Takemasa Miyoshi. Professor Rega, who is here, well, he doesn't really need an introduction because Professor Rega has been around for decades. He is our emeritus professor of nonlinear dynamics and structural mechanics at Sapienza, so he will introduce our keynote speaker. Thank you, Professor Giuseppe.
Thank you, Walter. Good morning. Good morning to all of you. After this wonderful artistic and musical introduction, we started the scientific program with the first keynote on a very hot and challenging topic, which is weather dynamics, which is a field where nonlinear dynamics and control can furnish all their potential. Professor Miyoshi got his bachelor in theoretical physics and nonlinear dynamics from Kyoto University, and then his master and PhD in meteorology on ensemble data assimilation in Maryland. Since 2012, he has been leading the data assimilation research team in the RIKEN Center for Computational Science, where he is now. And he was a chief scientist and deputy director. He has published more than 140 peer-reviewed publications, a lot of invited conference presentations, including the core science keynote at the American Meteorological Society annual meeting in 2012. And then he got a lot of awards: Japan Geoscience Union Nishida Prize, Yomiuri Gold Medal Prize, commendation by the Prime Minister for Disaster Prevention, and award for Science and Technology by the Ministry of Education, Culture and Science. So please, Dr.
Thank you very much. And thank you very much for the organizers for inviting me to be here. It's really a memorable and impressive start of the conference, and I'm really pleased to give this first keynote today. And I'm really new to this community, so let me first start with my brief introduction. So this is a work I have been recently working on, the controllability of extreme weather. So I graduated from the Kyoto University and I got a bachelor's degree, and then I immediately started working for the Japanese government. That's Weather Service of Japan. JMA stands for the Japanese Meteorological Agency, and where I started developing numerical weather prediction system for operational weather service using a supercomputer. And my role was to develop the future generation data assimilation system. And I had a chance to study at the University of Maryland as part of the government employee training program. And I had the exact 2 years for this graduate study. I was supposed to finish my master's degree for 2 years, but I also finished my PhD thesis in that 2 years. I heard that's a record of the University of Maryland because, well, theoretically, it's impossible to be faster. No one knows if there was someone faster than that. But then I returned to Japan to develop the future generation data assimilation system that I studied at the University of Maryland. And I decided to move to academia. And I was a faculty and assistant professor at the University of Maryland for 4 years. And then I decided to move to Japan when Japan developed the fastest supercomputer in the world at that time. The computer was called K computer, now replaced to Fugaku. That was ranked #1 until last year, I think, and now it's ranked #2. So I was fortunate to have an access to this supercomputer, and I have a lot of work that I can talk to you, but I skip all of them, and I focus on the recent study about the controllability. So I'm leading the data simulation research in RIKEN. I'm also a chief scientist, and I'm also a deputy director of the interdisciplinary theoretical and mathematical sciences program of RIKEN. Okay, so sorry for this handwriting picture. So we have the small uncertainties at initial time here, and then it grows exponentially. I assume that all of you here are familiar with this phenomena of the sensitivity to the initial states. So this implies, well, the limit to predictability. So that's what we have been working, well, my background is meteorology, so all meteorologists try to predict the weather, but because of the chaos, the predictability is limited. So we focused on just to understand the predictability and improve the weather prediction. The chaos, implies the limit to predictability, so we cannot predict the future well. But if we know what direction to go, we could choose a particular orbit. Even though we cannot predict the far future, we can predict near future. And if you know which way to push, we could choose a desired scenario. Let's say the amount of the rain. If we would like to avoid the heavy rain, we just try to push the atmosphere to less rain to avoid the disaster. So to study the weather predictability, the OSSE observing system simulation experiment is a well-known approach. I will describe briefly what is the method of this OSSE. So we first assume a nature run. We don't know the exact nature, but here, this is a simulation study. So we just run a weather model, very accurate weather model, to represent the nature. So the nature is known, but we have a system that is blind to the nature. So what we can know from the nature is a limited information, usually noisy and sparse representation of the nature. Those are the observations that we simulate. And we have a system for the weather prediction, the forecast system, blind to the nature run. So the forecast system never knows the nature run, but they can know the observations. Those observations are limited and noisy. So we have parallel representations like this. So we call this the ensemble states. So we have ensemble, 4 ensemble members, and we apply a Bayesian statistics to include this simulated observation and update the states. So that process known as the analysis. And we repeat the same process as we get that observation. Then we keep track on the nature. We never know what is the nature, exact nature, but we can keep the track on the nature. And we can evaluate the accuracy of a prediction system or the value of the observation data using this framework that we have been doing. For example, we had this heavy rainfall event that killed about 100 people in the western side of Japan. So this heavy rain was really difficult to predict. So we simulated this case, and we assumed a new observing network like that. The right side is a nature run. So we never know what is a nature. But on the left side, we have a prediction system that tries to predict what happened in the nature. And the prediction system is not perfect. So the rain location is a little bit shifted towards the south. And we have an observation simulated based on the nature run. And if we assimilate those observations, into this prediction system, then we get in the middle. So we have the right intensity and the location of the precipitation. That's where the heavy disaster occurred. So this implies that if we have that observation network, we could improve the prediction. So that this is a kind of study that we have been doing in meteorology. So now we think about changing the nature. So we have the same system. We do the data assimilation like this, and then we try to change the nature because we know that the nature sometimes causes disaster. So in this case, we assume that the upper side is an undesired future, and the lower side is a desired future. And if we can identify what is desirable, we could push the system like this. So we take the difference. This difference may be too big, so we rescale to make it small. And then we apply this change to the nature. Again, the nature is unknown to the system. But we know that as long as this system works, the nature is somewhere within our predictable range, right? And then we push the system, the nature system, to down like that. Then we can change nature like that, okay? And then we observe the new nature because that black line never occurs because we change the nature. Then we have the new nature, then we can observe that nature. Then we do the same data assimilation. Then we forecast, and we can repeat like that. So this is how we can choose the better track of the weather system, or whatever system it is, this method is applicable. Okay, so first we apply this method to the Lorenz, famous Lorenz model. So this model is, quite often used in meteorology. You know, the Lorenz, Ed Lorenz is a meteorologist, and he developed this model and found this strong sensitivity to the initial condition. Okay? So here what we did. So we have the initial state estimated by the ensemble data assimilation system. And we run 3 ensemble members. We know that this system has 3 dimensions, and 3 ensemble members is good enough to represent the error structures for the Bayesian estimate. So we could perform the data assimilation stably with 3 ensemble members. So these blue lines are 3 ensemble members. We have the initial time 0, and we predict for 300 steps. Well, not steps, it's 300 time. And we see that these 2 lines, the blue lines, go down, and 1 line stays up. And we set the goal of the control in this case to stay on the positive x side. So that line 0 here, upper side is positive x, and lower side is negative x. And we know that the system is chaotic, so that we cannot predict when exactly the state shifts to the other regime. So we try to keep the system stay on the positive regime. And this is a prediction suggesting that we will have the shift of the regime at 300. So then we apply the control inputs for this short time period here, because we get the next data at this time. So we apply that, and then we see, in this case, the black curve is a nature run, and the red curve is a new nature run with control. So in this case, it was successful. But again, our system is blind to the nature, so we never know what is the exact nature. But we are hoping that we can control like that. Okay, so there are 2 parameters. One is the forecast length, t, to determine when we identify the regime shift in our ensemble forecast. And the other parameter is D, that's the amplitude of the control inputs. Okay, so the left side is the normal case, and the right side is after we apply the control. So in this case, with the proper choice of T and D, those are the two parameters, it stays on the right side forever. So it never shifts to the left. Okay, that's the positive X side. And the arrows, the vectors indicate what kind of control signals, the control inputs that we apply. So this is a vector computed from the ensemble, taking the difference of two ensembles. It's very effective, like this. And we see the top left is adding the control inputs to all three variables. And T and D are the two parameters. So the D is the amplitude. So if we make the amplitude bigger, it seems more effective, but less effective if we add two big control inputs. And this side here is the forecast length. And it's clearly effective if you have longer forecast time to decide if you apply the control inputs. And all the other panels here are the partial inputs. Even this one, that only Z, we know that this system will not synchronize if we just synchronize Z. But just adding the control inputs to this variable Z is quite effective to make it control very effectively. Okay? And then we extended this study to a little more complicated Lorenz 96 model. And actually, this was published today, like an hour ago. And we did a press release at that time. So this is quite fresh. So the Lorenz 96 model is like that, the equation like that. And we have 40 variables. It can be the K variables, any K can work, but we decided to use K is 40. And OK, so it's like a circle. And arbitrary quantity like X evolve in time. And if you run for 1 year equivalent, this is 1 year equivalent, and 40 variables, so this shows all variables for 1 year, we can identify extreme large values. So we just assume this is in extreme events, twice a year extremes. And the right side is a 100-year histogram of these values. And we can identify what is the threshold for the twice a year, well, reducing heavy rain, something like that. So, or decreasing the tropical cyclone, like hurricane intensity, something like that. So that's why we try to use this model to represent some arbitrary variable that can reach to a very high value just twice a year. So we run a forecast. The top side is our prediction system. So we never know the true, the nature state, but we have a prediction system that we know that our system is reliable to some extent for making the prediction. So from this time, there is no extreme value predicted. But using this observation at this time, we update the state and run the forecast, and we identify here, we get the extreme. So this is just a prediction. We never know if it really happens, but at least the prediction tells us there is some potential probability that we get the extreme. And we would like to avoid this extreme, so we apply the perturbation here to the nature. So this is a nature run. And in this case, this nature run actually hit the extreme. And we push it down, then we avoid the extreme. It goes close, but we can avoid it. And this is a histogram. Again, there are two parameters, the length of the forecast to decide if we identify the extremity of prediction, and the D, that's the amplitude of our perturbation to add to the nature. So these white bars are the original histogram for 100 years. And blue bars are under the control case. So if you apply the control, we can avoid those extreme values happening more effectively if you have larger amplitude and longer forecast. But it's shown that it's quite effective. And we also thought about the perturbation energy, because we would like to minimize the energy inputs to the system. So we changed the parameter. This alpha is the perturbation D. And if you have, well, we would like to keep the high success rate. And if we have smaller alpha, we can reduce the perturbation energy in general. And we also try to limit ourselves to control only locally, not the global, all 40 variables, but add only like 3 or 4 local parameters. And that is also effective. The random choice, compare with the random choice here in the middle. The neighbor sites is more effective here. The success rate is very high with the neighbor sites. The neighbor sites mean that the neighbor of the extreme event happening. So we identify where the extreme event will happen, and we limit ourselves only within the neighbor of like 11 points. And then we can reduce the perturbation energy significantly. And the method is general. So as I said, I'm a meteorologist, and we have a big supercomputer. So we can run the real atmospheric model like that. So we have a typhoon hitting Japan. We would like to avoid the heavy rain in Japan. And if we apply the same method, we could effectively reduce the intensity. This is the intensity measure. And this is the original typhoon. It's very intense, but we can reduce significantly the intensity. Oh, the heavy rain, the local heavy rain case. This is the actual case actually happened in Hiroshima in July 2014. We had a heavy rain, and some part of Hiroshima was completely destroyed, and a lot of people died at that time. And this was the actual case, and if we applied, so this is just a simulation. Applied, we could reduce the rain peak and also shifted the location of the rain. So this seems effective. And we also explored how much energy to put. This is energy measure watts, and this is 1 gigawatts. 1 gigawatt is usually equivalent to 1 nuclear power plant, or the big power plant, basically. So this is somewhat human's capability. The nature run shows a heavy rain, like 200 millimeters rain. And if you apply small perturbation, but still 1 gigawatts equivalent of perturbations, we could reduce the rain like a little bit. But this a little bit may be critical. So, but if you apply even bigger amplitude, we could reduce quite significantly. The figure that I showed in the previous slide is a case where we added all perturbations. So that was really big. So this is something that we are exploring, comparing with, well, combining with our actual technology to put perturbation to the atmosphere. Okay, so this is the last part. We also explore a control method by reinforcement learning. So in the previous study using the Lorenz model, we identify the control inputs based on 2 ensemble members. One is a good scenario, the other is a bad scenario. We just compare them. But now we apply reinforcement learning, so purely data-driven, to find what will be the effective actions to make. So in this case, we tried to solve this problem. Can we control the chaos by enhancing the chaos? Enhancing the chaos means that this model is based on this convective system. So we know if we change this rho, we can enhance the chaos. So this is the choice of rho. And if rho is less than 24.7, it's non-chaotic. But if you increase rho, that means it increases the instability. So we enhance the chaos. And the normal choice is 28. So it's chaotic regime. But we added 1% of perturbation of rho. So increase it. That means it enhances the chaotic behavior. And then we just use the reinforcement learning algorithm to find out the effective actions. These are the parameters. I will skip the details. So the left side is control off and the right side is on. It's perfect. So reinforcement learning is really efficient or effective. But this is a black box. We don't know what this thing is doing. So we open the black box. We try to understand how it works. So the left side figure on the bottom, it's a control off case. The right side is control on. And this red line indicates the value of rho. So if you fix the value of rho 28, of course, this is a chaotic Lorenz model. So it shifts to the other regime randomly. But here we increase 1% the value of rho at this time. Then it keeps almost periodic orbit. So how can it be possible? Let me skip this. Oh, okay. I don't skip this. So we have a fixed point, but this is unstable fixed point. So there is a spiral motion. And changing the rho corresponds to changing the fixed point. So if you change rho slightly, we shift the fixed point a little bit. Although we enhance the chaotic behavior, that means that we have more growth of the error. So okay. I guess this figure says by itself. And what we do is just we choose the proper timing to change the rho like that. Then we change the orbit at the time that we change the value of rho. So we can choose where exactly we choose the red orbit and the black orbit. That corresponds to the reinforcement learning finding the proper timing. Okay? So, yeah, this implies the generalization because many systems have the similar situation like this, because we usually have some fixed point, and the fixed point becomes unstable and becomes chaotic. And if you know how to change the fixed point, we could apply the same method for other systems as well. So yes, we could suppress the chaos by enhancing it. And the reinforcement learning was very nice to find the chaos control strategy. And now we are working on applying this method to a typhoon model to control the typhoon development. Okay? We also developed this interactive web page for the control. You can see the bottom right. We can change the value like that, and you can play with this. So if you access there, you could play with this thing. Okay? As I said, we also apply this method to the typhoon control. So the typhoon develops, so this is the maximum wind of the typhoon, so it becomes very intense. But in the maximum intensity stage, we could apply, in this case, reducing the sea surface temperature in a limited region, where to change the sea surface temperature, and we could change the intensity like that. And all of that, actually, the study that we did led to a big decision of the Japanese government, Moonshot Research and Development Program. So they set a new goal, Moonshot goal number 8. This is a relatively big size of science project in Japan, led by the Cabinet Office of Prime Minister. It's basically, well, control and modify the weather by 2050 to avoid the extreme winds and rains. And because of the study that I did led to the discussion to set this goal, I'm now appointed as the program director. The program director is not a role to do the research by myself. I really would like to do the research by myself, but now I'm managing this only part of my time. I still continue my theoretical research. Okay, thank you very much for your attention.
Thank you very much. Very interesting talk. So the talk is open for questions, comments.
Can I ask a very quick question, actually two? So you use reinforcement learning, right, to do the control. So have you looked at the meaning of the periodicity of this periodic variation in rho in terms of changing the equilibrium point? And then when you talk about control energy, what is the control input, like physical control input?
In this case, the control input is to increase the temperature gradient from the bottom to the top. So that means that we heat the bottom or cool the bottom, something like that. Periodic, yeah. So that's a periodicity. So we know the period, so we shift the circle so that it's not a closed circle, but we can make it a closed circle by shifting the origin of the circle, the center of the circle.
Yes, please. Please.
Oh, okay, thank you. Very interesting talk, thank you. A question about especially the complex models, you're talking about actual temperature and so on. Can you speak to the limit of or the effect of model uncertainty on the effect, on doing this, and also in terms of the prediction time?
Okay, thank you very much. That's a really important point, particularly if you think about the real-world application of weather modification. So we need to have a model accurate enough, reliable enough, so that the model represents the real nature in a reliable way. So we know the weakness of the current weather models, mainly about the cloud formation part. So if we have a control action necessary about the cloud formation part, the seeding is usually the case, and the model may not be as reliable. So in that case, we need to be careful. So, but the thing is that all of these control actions based on our model performance. So it's really important if you think about the real-world applications that we have the model reliable enough to make proper decisions. That's a very important point.
Thank you for the talk. A related question. What is the relationship between the frequency of control input to success rate? So have you looked at basically increasing the success rate, avoiding unintentional outcomes, and the relationship of that to level of control input and the frequency of control input?
So for the moment, we focus on these two parameters. That's the length of the forecast and the size, the amplitude of the control inputs. And the larger it's not necessarily the larger the inputs, the better controllability. So we have some optimal point of the input signal. And for the forecast length, the same thing. If you focus too long, then it's completely chaotic and it doesn't make sense. So we need to set the proper length so that we have the predictability of those extreme events happening or not. We can decide if this might happen, then we can activate the control inputs. So those are the things that we explored so far. So the side effect we didn't look at yet, and it's really critical, crucially important if you think about the real-world applications, what can be potential side effects that might be caused. Thank you very much for that point.
It's a follow-on. There's basically the same sort of question, but I was curious. This is a very local sort of analysis and approach, and I'm just concerned about how does it spill over? What's the equivalent control spillover? You know, what's it going to do to us in another part of the world?
Thank you very much. So the method is general, and we can apply it to any parts of the world if necessary. And the consequence we need to evaluate very carefully. For example, if we weaken all intense typhoons, that means that the typhoons usually propagate the energy from the south to north, and we may have more typhoons or those, and we need to evaluate. So that's something that we have to address in the future. So basically, we choose the orbit of chaotic regimes. So there is no, nothing, we don't change the mean state. We don't change the climate. We just change the local weather. That's the idea.
Okay, I'm sorry, we have to stop. There are other questions, but we have no time. And of course, after you will have...
we will have a coffee break after the second keynote. So thank you very much, Professor Miyoshi.